So we're going to continue our discussion of the analog between rotational dynamics, as it was developed by Euler and picked up by Lagrange and others, and as you learn in your first year here at mechanical engineering. And then something that economists think of as the theory of capital. So up to now, we've been dealing with commodities, and commodities, they live in the space. It's like just a space around us. And each good has an axis, a dimension, in which we call an account, where you keep track of how much you have or disposed of or acquired. All right. So all directions are kind of the same. One has got apples, the other is oranges, some is money. All of them are the same, and you can translate along them. Now, in the theory of capital, what happens is we take one of these dimensions and treat it qualitatively different. All right. So the classic example is land. Of course, you can think of it as a commodity, but it really isn't. All right. You can't produce much of it. It tends to be stable. And what it does is you use it to produce commodities, right? So this goes back to the days of farming. Before farming, when we were hunter-gatherer, probably everything was a commodity. You just hunt for some meat or you gather some berries. But when people started settling down, land was treated separately. All right? It was just some asset you had. You couldn't eat it itself. You couldn't eat the land, unlike these berries or this meat, but you could use it to generate capital. And a big issue in economics was always, why does land have value since you can't eat it? It's like, why does money have value if you can't eat it? All right? You don't need it for life. Okay? And this was first done by Ricardo. It was a while ago, a few hundred years ago. He was a Dutchman, actually, but he moved to England pretty early on in his life, or maybe his parents even moved. And he came up with the first theory of capital. And he posited that land did not have value by itself, but only had value because it could produce other goods. So that's different than apples. Apples have value because they're fun to eat. Okay? Land has value because you can put an orchard on it, and from it, you get apples, which you can eat. And this concept of capital that starts with land, then starts extending. So I think in the 16th century, especially in Holland here, there was a new form of capital, which are ships. Because ships, you can't eat them either, but you could use them to go to the Far East and get the spices and bring them back, which, now you sell, and then you get money so you can buy food. All right, so the ships become a form of capital. After that, you get the Industrial Revolution, and then machines become the form of capital. And then information becomes also a form of capital. In the meantime, also, I think in the Middle Ages, they only had land and then labor as a form of capital. Okay, so they had another one called labor. We don't really think of it as capital now, but traditionally it should be, and it's a human capital or something. All right? Okay? So there is something that's different about capital in that if you have it, you get the returns. All right? Okay? Sometimes that's called an asset, but an asset is a little bit more general because you can also have an inventory of apples and it's still an asset. Okay? Okay. Now, how this capital gets priced is a separate issue. All right? And that's what economists have several theories about it. You can read up about that by yourself. What we're going to do is map those theories into rotational dynamics. So rotational dynamics is also a kind of an interesting story because dynamics begins with just Newton's mechanics. And in Newton, there's a point particle. Nothing is rotating, and it's just translating in three directions. Okay? That's it. Or you can have a cloud of point particles. Each of them has three directions. So if you have n point particles, you have n times three dimensions. All right? All kind of the same, all buzzing around. Okay? Then Euler comes around, and Euler he derives that for rotating bodies, you have a similar law. You replace force by torque, you replace mass by moment of inertia, and you replace velocity by angular momentum, angular velocity. All right? So you just figured out it ends up to be the same. It's a bit of a calculation, and we'll do it later. All right? And it just ends up to be the same. That's kind of magical. Okay, great. Now we can do it, and we're engineers. Thank you, Euler. Let's go calculate. All right? Then later on, people started wondering, well, are there other extensions to this? Not rotations, but other things. And in fact, Einstein found one that's called a boost, So in general, in special relativity, you have a sort of translation, a sort of rotation. It's a hyperbolic rotation, all right? And still, you can have momentum and that kind of things, all right? And then some other people, especially mathematicians, developed a theory in full generality, just like Arnold and Marsden and Weinstein. And they use a quite an advanced theory called Lie group theory. And we won't be using that, but we'll do it in the spirit of Lie group theory, because the ideas become all of a sudden very simple. But if you have to read the math text, you get these books on geometry without a single picture. And this is not something that I feel is readable. All right? Now, what we're going to do is say, all right, this capital is preserved in some way, all right? So it doesn't change on the same time scale as the commodities that it produces. So this preservation, the best way to identify that is through symmetries, right? So if you have a rotation, the symmetry, then you have a radius, this conserved quantity, and then the symmetry are all the rotations, okay? So we start acting with a group of transformations, either rotations or translations or things like that, and we're going to figure out what the conserved quantities are. We talked about that last week, or 2 weeks ago, I actually believe. And here I made a small list, what we're going to see. We first went through commodities, and we looked at it from a different perspective. So we said, okay, how can we get a commodity theory without writing everything down? Well, all we have to note, really, is that in a commodity theory, we can imagine that we do the same kind of dynamics, but then at a different stock level, okay? So say I'm buying 5 apples a day, and I do it in the beginning of my life after I've, I don't know, I'm, at 24 or something. Then I've eaten so many apples, and I'm doing this. Or I can do it at 28, and why would anything change, right? Just because I've been eating, had a lot of apples beforehand, I'm still going to look at this at the same thing. I'm just going to go to the Albert and buy these apples, and nothing really changes if I didn't change, all right? Okay? So what this is really saying is that if your whole economic situation it doesn't depend on how much you've already consumed beforehand, right? Then there's a sort of invariance, meaning that any function, will be independent of whether you shift it over, right? In the stock level. Maybe I'm saying this way too complicated, okay? So look at this graph. Here is the price, and it's determined by the quantity demanded. This is the velocity, right? How does this, and this is the price. You can look it up. This is how economists do this, all right? Now, how does this price depend on how much has been bought before? It does not. According to this graph, all you need is how much are you demanding now, not how much were you demanding yesterday or anyway in the history. That's what's implied by this graph, you see? So how much you've bought before, right, is irrelevant, okay? So I can shift the whole thing, and I'll still have the same law of demand and supply, okay? So the laws of economics are invariant under shifts, okay? So you'll say the theory of demand applies when I'm 24, but it also applies when I'm 48, okay? It'll make a difference. That's the same in mechanics. So if you do some experiment, you do some F is M times A things, you have a little car and you push on it, so you get this kind of thing, you give it some momentum, you see what momentum is in equilibrium. Suppose I took this experiment and I did the same thing in the building over there, at whatever the guys are sitting there. Would that experiment come out any different? No, right? It was the same thing, okay? So you see, this is the idea. Now, if you work through that, and we'll do this later for capital, you'll see that if you do that, there's going to be something that is a constant. And in this case, it's the price. And this is exactly what they're saying. So these symmetries imply something that's constant, and that's going to be this price. Okay? Yeah, because the price is a function of how much you've done, and it's invariant on it, so it has to be constant in Q. All right? Can change in T in time, but not in Q. Okay? This is the idea. Now, Newton didn't do it this way, so Newton just wrote down the laws, and then you can figure out that what that means is that if you write down P as M times V, that obviously the value of Q is not going to be relevant for determining this. All right? Huh? Okay. But this is the key to generalization. Then that's what we're going to do with the theory of capital. Okay? Now, because we want to treat capital differently than all other goods, we don't use just regular Cartesian coordinates. We use something called polar coordinates. Now, you all know polar coordinates. You got a pole, that's right in the center here, right? And then you got this polar axis, there's a certain length, and then you just swivel it around, right? And then you can extend this axis, but it's a different process from going around, right? So on the Earth, you can look polar coordinates and you're moving every which way, but the radius of the Earth is relatively constant, so, you take the arc or the row or whatever, arc coordinate, that's the length. Now that's the set of coordinates we use for the theory of capital, right? So we're going to assume that there's an axis. And here I got a very simple theory of capital. So I got some land over here. I'll call that Q0. And I got some crop over there. I'll call it Q1. And I'll fix the amount of land here in green. And then you just start producing your goods and you're coming along here. All right? So this is the pole. All right? Now, if you move over here, what's happening is you can see this thing moving like that. And this thing is kind of the same. But you'll keep this as the pole. So if you draw this line, you just got to see that this distance is kind of just the same as that distance. All right? That's just the way you think of it. It's obviously not the Euclidean distance, this squared plus this square root. All right? It's sort of a distance. In a different metric, different way of measuring it, where you ignore this length. Okay. So this is a simple set of polar coordinates, and then what you do is you can calculate an angle and an angular velocity, So I'll take how many apples I get out of here divided by the hectares, and I do exactly what you would do when you want to calculate the angular velocity. All right? You just take this. You have to take this distance here divided by there. And then a radian is then, you just try to fit in r here. Then you have 1 radian, because that's how many times your radius fits in there. All right? Now, this is a little bit tricky, of course, because these may have different units like bushels, and this may be hectares or something. And you'll get bushels per hectares. That's a little bit tricky, but it's okay, right? Typically, what they'll do is they'll try to get these things to have the same unit. So they'll use what they call the reseed ratio. There's how many seeds you need per hectare, and they use that. And here are the number of seeds, and then you divide, and then it's a dimensionless number for the angle, and the angular velocity is. So you see, this is a very simple way of describing something you would call the yield. All right. Then you can extend the amount of land. I think last time we talked about it a bit, how this is interesting historically, you know, there's only two types of people, the ones who are into farming and they're going along this axis, and the ones who are doing the war, huh? And they're going along this axis, okay? And those are the groups of people. I have a few groups that got to bring this to the market or something, but very small, huh? Just the aristocracy, a peasantry. I think they have a third group that just does the talking, the priesthood or something, okay? But of course, if you get more forms of capital, it becomes, you get capitalists, there's a machinery, and you get, huh? It gets more complicated, all right? Your economy gets more complicated, okay? So the picture's clear, right? So let's start moving along. So here is the table, and I just want to step through the units of a few of these. So this is the one we did. So we have this, this dimension here, the Q0, this is Q1. So the capital is in hectares, it's just the amount of area, right? Arable area. Yeah? The Q1 is some crop, okay? And then the velocity, that's how many crops you get per year, right? I'm just measuring that in kilograms. So the velocity here, this velocity here, V, let's see, so many kilograms per year. And then the angular velocity is measured. You have to divide this by Q0, right? And to get the angular velocity. So you'll get kilograms per hectare per year, all right? So what does that mean, right? It's clear that what happens is if you had measured the hectares also in kilograms, all right, some kilogram equivalent, this would be 1/years, all right? That's what they do with the reseed ratio. So they say so many kilograms of seed per hectare is needed, so we'll measure hectares and seed. Then these units fall out and you just get a return of so much, okay? But otherwise, you're making so many kilograms per hectare per year, but this is not so crazy because this is really your productivity, right? So many kilograms of seeds per hectare is your productivity. So you have a rate at which your productivity is going, okay? So with all these things, if you just keep your mind screwed on, okay, it's all not so fanciful, all right? Okay? Here's another one. This is this industrial revolution. This PP&E, that's accountants lingo for property, plant, and equipment, okay? So there's all the machines and buildings and all of that. I've just measured it in machines. And what you do with a factory and with your machines is you make products, all right? Sort of a crop, okay? This was invented at the time. Nobody had thought of this, right? That you could have machines as capital, and then the product was not the crop, but it's interesting how these things then go in analog, you know? Like you have a ship and a pilot and a starboard and backboard, and then you will get an airplane that just use the same terminology. They also go to a port or an airport. And, It's the same thing here. They kind of borrow the terminology, all right? So the output, the production, I'll just call it output here, okay? But you can also call it the production. You know, it's the theory of production. They produce these things. But produce really was just the crop, huh? So there's so many items. So your output will be so many items per year. And this one, I made a mistake, right? So this should have been items per machine per year, right? So every per machine, so many items, that is your, okay? Economists will measure everything in money. So they'll measure this in euros, right? And there's this euros, and this becomes just a return. But the way they do it, I don't really like, because then they multiply by some price, okay? But then which price? So they'll take some past price, and they'll call it nominal output. but then the prices change, so they have to call it real output, you know, they get into a lot of trouble. So it's better to, just to keep this, or have some kind of receipt ratio thing that is just immutable, that doesn't change all the time, okay? Right. Here's another example that's kind of interesting, these things. So you have labor. So the capital is what? Well, that's your labor force, it's called. And these PS stands for persons, huh? So many men or women or whatever is doing the work. All right. Now, what is the product? Now, it's called labor services. That's the official name for it. In fact, there's a really nice project available. Several people also at Rabobank are interested in how to model these labor services and how to do that. They have a whole paper how they do it, and it's interesting to see how you can translate their models. They're all kinematic, and all we're doing here is kinematics into this kind of framework. And look at it as rotations, and once you see it as rotations, you can use our theory. All right. So this is called labor services. These are measured in person hours, or man hours traditionally. Okay, and that's right. You pay for so many man hours, right? So this thing over here is in man hours, and this thing over here is in men. Okay, you see that? Then the work, you have to divide the man hours by some time, all right? So now the interesting thing is the work, that's the output, right? That's so many man hours per hour, okay? That's just in persons again, right? So we talk about, work as being, okay, how much work can be done now? 5 men's worth, right? Or 5 people's worth of work, right? And that's the rate at which the labor services are being delivered, okay? It gets really confusing because you would think that you would confuse easily the labor force with the actual work, right? But it isn't, all right? These are the workers, and this is the work, which is the rate at which, okay? You see that? Then you can look at the productivity. So you divide this rate by the capital, and then the productivity is just has no dimensions at all. Whereas an angular velocity will be the inverse of time, right? So funny things happen. Okay, so keep your head all screwed all right when you're looking at a particular theory of capital. It all works out in the end, and it all makes sense, and it's all the way they describe it and use it, okay? But you can't just assume that your yield is in 1 over time, all right? Okay? But don't panic, just keep going through it, or here's another one. This is another thing people are interested in, housing, right? So the housing market is another thing the bank is very interested in, because if people want to buy less housing, they get less mortgages and they get all kinds of trouble, or great things are happening. So that also is a capital theory. So the housing themselves is capital. So you see, you can't really do anything with a house. You can't eat it, right? There's some people that walk around and they say bricks are always worth something. This is nonsense. It's not true. If you put those bricks in a place where nobody wants to eat, to live, like in the middle of the desert, they're absolutely worth nothing, right? Actually negative, because you have to pay tax on it or something. So this is, so the housing themselves, but it's the benefits of the housing. That's what we've called the housing services here, okay? Those are worth something. Why? Because the house provides you with protection against the rain, and you can sleep, and I don't know what you can do, right? All kinds of fun things. Everybody needs one. Okay? But it's the services, and they is measured in square meters over years. Okay, not per year. So if you get a hotel room, you'll get so many square meters over a day, right? A day's worth of one room, okay? Not per day, a day's worth of one room. If you rent a car, it's the same thing, right? Huh? Okay, you get this car, one car for 1 week, boom. Huh? So it's square meter month or something, all right? Huh? Not per month. But then if you look at the rates, the rent, that's called the rental, okay? Then you divide again, all right? Because you take this derivative, and then that's just so many square meters. So I'm renting so many square meters, but I'm receiving so many I got so many square meters this month, all right? That's what I have to pay for, okay? You see that? Maybe I'm beating a dead horse here, but it takes a while before you really keep it all apart, you see, because this and this is again at the same unit, so there's a huge confusion here, you know. And probably Bernard remembers when a lot of people were confused about this. What now is labor and what is work and what is this, okay? Then there's something these economists call the occupancy, and that's then the angular velocity, the yield. That's what they call the occupancy. Now, money is also an interesting thing. So money kind of has two purposes. If you go here, you can think of this as an interest-bearing account, all right? Not compounding, right? So this is the investment, say, or this is your deposit, I should say, and this is the interest. There's two different things, You can't put them all on one. It's two different ports you open. One for the deposits and one for the interest. They're not the same. The bank will keep track of how much interest you received and how many deposits. The taxman too. You pay tax on the interest, but you don't pay tax on deposits, all right? So they're separate. But they're both measured in euros, right? This is the euros, this is the euros, okay? So I call it here not the deposit, but the principal. So if you have a loan or something, it's called the principal. And this is the interest paid on it. They're both in dollars here, all right? So the interest receipts, that's of course the velocity. That's in so many dollars per year. That's an arrow going up. And now I'm going to divide that by the principal, and then I get the interest rate, okay? And that's in so many percent per year. You see? This is an example that should be familiar to all right? And as you see again, the mistake you make here is just because these are the same unit, you throw them together, right? So if you make your multi-port model, be sure you have a separate port for the principal and one for the interest, because if you throw it together, you'll lose. How do you even have leverage or anything, okay? So just because they have the same unit doesn't mean it's the same stuff. You know, if you have a plane, just because the x-coordinate and the y-coordinate have the same unit doesn't mean they're the same distance, you know? Okay, right? No, they're orthogonal distance. Securities is also an interesting thing that everybody knows. So you have shares, you can look at the number of shares, but typically what people do is they look at it at par or something, or and they call that the capitalization. Okay, agio in Dutch. This is, and they take the par value of the shares rather than counting the shares. Then shares that, if you have shares in a company, you get dividends out of it, right? Okay, there's an old saying: a cow for its milk, chicken for its egg, and a stock for its dividends. So the stock itself, you don't do anything with it. You own this piece of this company. When are you going to eat this, right? But you get the dividends. Nowadays, we would say earnings, because a lot of companies don't pay out dividends anymore for tax reasons, and they reinvest it. But you're the owner of all that cash that they're carrying. So you would say here earnings, okay? And that's a detail, okay? This is the earnings. Maybe I should use a different color, right? Let's put black. Oh no, let's go put TU Delft blue. Huh? There we go. Now, the dividend rate is, of course, the rate at which you're getting these dividends, okay? Or the earnings rate. Huh? Typically, people say that that's the earnings, huh? And then this is the total earnings received or something. You know, you got to be a little bit careful whether they mean the rate. Huh? Economists say earning and earnings, but I find it so complicated, okay? Huh? And then if you divide the dividend rate, so that's how many dollars per year you're receiving in dividends by the number of shares, then you get your rate of return, huh? Okay, on the stock. Okay, so again, you see, this is this idea of a yield being 1 over year. It comes kind of from when you can treat both things having the same units. And you'll see people monkey it up usually, so you can't. But in these theories here, they certainly don't. Okay. This is the terminology used. So you just got to keep your head screwed on right. Okay. But it's clear that these are all really valid examples of the theory of capital. So if you look at this, you wonder what you can do without this theory. I mean, you sit there with the commodity theory, it's nice and well, but everybody has got a piece of land going on, huh? Okay? And that's the way you look at it. So as soon as you have a labor market, a housing market, look, of course you can just focus on this thing and somehow just model that and then ignore it. But a good model will take care of how the labor force is growing and stuff like that. Okay? All right. So these are just some examples. Keep this in your head, right? So, all right. So now let's start getting creative and looking at these various types of symmetry. Okay. So this is the one we already did, right? So we have this land, and you fix the land, and it's an inelastic resource, you know, and this thing is kind of going orthogonal to it. So we'll think of this as orthogonal, but this also as orthogonal, you know? Huh? It's a little bit weird, but go along with me, all right? Huh? Now I put 2 other examples here. These are really classic. So this, of course, you recognize immediately. This is what we would normally call rotations, but these are also rotations. These are called hyperbolic rotations. So here you use sines and cosines, and here you use sinh and cosh, all right? You may have learned these in, what is it, Analyse or something, and then never use them, right? Yeah? I think that's the case, no? But we'll use them here, okay? So, in fact, this is also a sort of a sine and a cosine, right? I think we talked about it last time. So for a small angle, you know the cosine is about 1. So this is the cosine, it's always 1, right? And for a small angle, the sine is just, you know, proportional to the thing. You know, that's precisely what's going on here, okay? We'll talk about this a lot more. I just want to say, this is just the first step of totally generalizing this to symmetries, okay? And what you see is that there's 2 things. There's like your kind of your capital, which I'm going to call this radius r, all right? That doesn't change. I mean, it could change, but to first order, it doesn't change. We keep it fixed, okay? And then there is this thing of the return, and these are perpendicular to each other, okay? In this case. Here they're not really perpendicular, but and here they're also kind of perpendicular, but they're hyperbolically perpendicular. We'll get to this, okay? That's why you see, sometimes I will say it's orthogonal because it sounds a little fancier. Perpendicular, you think of a really square, right? The way you got to think of it is that all of these things are kind of circles. And how do you define orthogonality? Well, you first have a circle, then you draw this line, right? Then you look at when this line goes through the circle, and then you draw the tangent vector to that circle or that shape, all right? That's how you can define orthogonality. You see, that's how it is. Okay. Normally you define it with this inner product. Don't do that. Just look at this. If you have a circle, you can find the center. If you have a center, you can draw a ray out. Okay. You can look where it intersects the circle. You know what parallel means. All you want to do is define orthogonal. You know what parallel means. Okay. You know, it's just tangential. Take the derivative of a motion along it, and that is then, those two are then orthogonal. Now, so if I play the same trick here, I have a circle, it's this, so it's just a circle broken open, and I draw this line, and where it goes through, I go here, and I declare this to be orthogonal. Okay? If I have a hyperbola, I play the same trick. So here's my hyperbola. I draw this line, whoop, it goes through the hyperbola like this. This thing is then tangent to the hyperbola, and I declare this to be the orthogonal thing. All right? Now, remember when we had commodity space and we started drawing it like this, right? As if it's an orthogonal space. Well, we didn't know that this was orthogonal. In fact, we said we don't even know. I mean, there are no angles. So you see, by introducing a figure like this, like a circle, or this, by introducing capital as a mutical, we can define this idea of an angle, okay? Before, we only knew when things were parallel, all right? Because you're just buying only apples. So you have so many pairs here, you're buying only apples, you go this way, this way. But if I plotted the same thing like this, it will be the same, right? Huh? Okay? Because all we know is these are parallel. But now we can also define when things are orthogonal. And you'll see we can also define all the angles in between, okay? So we've got some extra structure. Now, Euclidean space, of course, we think of as being, having an angle, but that's only because we allow it to be invariant in the rotation. So if I take this laptop and I turn it around, and I ask you, is the same laptop? You'll say, yeah, all right, okay? Why? Because you think it doesn't matter how we rotated it. But if I stretched out this laptop, then you wouldn't say it's the same laptop as a stretched out laptop, you know? If I weirdly stretch it out. You might still do it because perspective actually does a scaling. So you will think it's the same laptop a little further away or looked at an angle. Huh? But there are definitely transformations you can do, like make a blob out of it, then it's not the same laptop anymore, all right? Huh? But rotating is, you don't care. I can take you, rotate you, right? You'll be the same guy upside down, right? Huh? What? Rather not, right? Huh? So we already built in that we can rotate stuff, okay? Our theory of capital is built in already in Euclidean space. That's why Euler was able to do this. Right? Take a rigid body and rotate it. I say, okay, I have angular momentum. But in relativity, you see, there's another problem. Like this will be space, and this will be time, and you can't just rotate from space to time. You got to boost. Okay, maybe you know that, maybe you don't. But you can actually exchange space for time or time for space, right? So if you go faster, you know, space contracts and time is longer, all right? It takes longer. If you go super fast, then time stops altogether. Okay, so there's a sort of rotation, and it's a hyperbolic rotation like this. This will be the speed of light, you know. Okay? So you can switch, you can move, take more space, and then you'll need this more time. So that has a different structure than Euclidean space. So every space has its own structure. You got to find out what it is, and that's the same with this theory of capital. So you look at the structure, and then you know what it is, and then you can start doing dynamics. But you first got to like figure out what the structure is, okay? Now, there's another thing you can do, and this is kind of a trick I use. I can now define this R completely different for each case and still use the same theory and the same letters, you see. That's the trick I want to do, because otherwise I got to do this theory, then this theory, and this, and calculate all these different prices for you, and I don't want to do that, right? So we want to have one theory. So I just need a new R and a new V. So this is my new V, right? This is my yield, It's going this way. Huh? That was here, and this is there. And here is my capital. It's just a regular radius. Okay? We'll talk about exactly what this means. Here you'll see it's actually this formula, which is that. Okay? And here it just happens to be this formula. Okay? So this is a hyperbolic radius. This is sometimes called a limit radius because this one is kind of in between these, right? So you make this thing bigger and bigger, and then it flips in this, and then you start moving like that, and then here, and then there's here another one, right? So it's kind of, huh? Sometimes it's interesting to think of that, okay? So you can move one to the other. You see that in second order systems, huh? So if it's underdamped, it makes a circular motion, huh? E to the I, whatever. And then as you increase the damping, it kind of starts going like this, and this is like critical damping, all right? And then overdamped, you get these kind of exponentials, okay? Okay, that's the geometry. Let's now look at some examples when this happens and when this happens, okay? So I wrote down here one example with chicken and eggs, okay? So we already said it, a chicken for its eggs, right? Now, what happens when you have a chicken farm? I never had a chicken farm, but I've heard that what happens is you have chickens, okay? And the whole point of these chickens is not to eat them, but to have them lay eggs, all right? But these chickens, they also die. And then you need to keep enough eggs in order to hatch new chickens, which then can lay eggs, okay? Now, I'm just now looking at a bunch of chickens laying eggs and living in subsistence. So we're not going to take any eggs out of there. And we'll just assume that the chicken population is not growing. I just want to step through what's happening there, all right? So we'll start off with this one chicken, all right? But of course, these are a gazillion chickens. I don't care, right? But if, imagine one bushel of chickens, one, how do you call that? I don't know, a kennel of chickens? A pen. Huh? What? No, a flock of birds, man. It's a pen. I think it's a chicken coop. The coop. Yeah, it's a chicken coop. I don't know, what's it in Dutch? Huh? I don't know. Nee, maar er zit zo'n heel groot ding, toch? Huh? Chicken coop. Ja, legbatterij. Legbatterij. Ja, dat is een legbatterij. Huh? So what happens is, at step one, say, this chicken produces an egg. So you're here, right? Huh? Okay. Now, suppose there are two chickens or something, right? So then half these chickens, this chicken dies after he laid his egg. All right? Huh? Okay. Then you one of these eggs is starting to hatch, right? Huh? Becomes a little kuiken, a little chicklet, right? It's not a chicken yet. Huh? And so you're losing one of these eggs, and another chicken dies. So you come over here, and then this goes on, and then when you're here, you're at your zero level. That doesn't have to be a real zero. Say 1,000 eggs here, and this is 0, and this is 2,000. I don't know how it works. Huh? Okay, so you see, you cycle your way around like this. Okay. You can also have calves and cows. You have a cow, and a calf is born, and then the cow dies, and this calf has to grow up, right? And then turns into a new cow, and it turns around. All right? Huh? So this is what they see. Okay? So you make this kind of circular motion when you have, and this is sometimes called amortizing. It comes from more, which means death, right? So your capital amortizes, okay? That means it dies off while you're using it. You use it also for real capital. So a machine, and you amortize it, meaning it's slowly dying, right? Huh? But capital doesn't really regenerate itself like a chicken regenerates itself for human beings or something, okay? So you go through these kind of cycles, okay? You know this? Well, no, because this is chicken per egg, right? Huh? Yeah, so it's a little bit weird. So what you do you will just say probably that each egg is a chicken, you know, and say this represents a chicken, you know. So so many chickens worth of eggs, right? Something like that to get it to be unitless. You don't have to, huh? You see, but that's what you would do probably. I mean, you have cows and calves, and I don't know, they're the same animal. You can think of it as the same, huh? So you got to monkey around a bit with the units, and then you can get it to be dimensionless. All right. Otherwise, you can't really use this formula. You know, this you got to put some factor here. You know, so you get this thing right. So it will be a little bit deformed, right? Huh? Okay. And then you got to like squeeze it in a bit. You get an oval, huh? So I made it here so that it's perfectly symmetrical. Okay. So with that thing, you kind of slap it down by doing, I don't know, A this times B that, you know, something like that. Okay. Because you can't really add oranges to apples or chickens to eggs. So you got to be a little bit, okay? Huh? That's a good question. My point for now is, I want to come and do this for banking too. But my point for now is just that this is the picture of amortization, okay? It's when you have these kind of cycles, okay? Now this thing we already did. This is just the regular production. And this is something that they call growth. So suppose you have, so economists do this, and I kind of took their examples. I'm not so sure about it, but this is what they typically do. So they'll have some machines, okay? So this is then the property, plant, and equipment, okay? And these are the products you're making, okay? So you have these machines, and you make so many products here, chop, huh? And then what you do is you take these products and somehow you're making more machines. So you do a reinvestment. So you go not back, but you add to your machine park an amount. You see? And then with this bigger set of machines, you make some more products and you'll make more. And then you add that too. That's called a reinvestment. Okay? You can do that also with dividends, right? So you get these dividends and then you reinvest them and you buy stock with those dividends, okay? And when you do that, you'll see that you're moving on like this. Just here you would move on, you know, huh? Back, huh? So here the stuff keeps dying and there the stuff gets reinvested and lives forever, okay? Now, if you do this, we'll show you in a little bit, you get something called exponential growth. I'll show that in a little bit. This one we all know is a complex exponential, right? E to the I theta. Huh? This one is also an exponential. We'll look at it later. It's a little bit hard to imagine why, but I'll show you. So there's these three different pictures, okay? This is really classic theory. So there's an interesting part of history also in geometry. So people used to think that Euclidean geometry was the only geometry. You could just go in straight lines. Actually, Euclid thought that. And he did a really good job. He wrote this thing a long time ago. And then for a long time, they just said, all right, this is just how space is, you know, and you measure the length of the line. And then in the 19th century, there's a couple of clever people, for instance, Felix Klein and was one, and Riemann, I think, is the other, who realized that you could have other types of geometry rather than just Euclidean geometry. And they came up with this geometry of a sphere, right? This is like a sphere, a one-dimensional sphere. So, you know, the shortest distance in space is a straight line, right? We all know that, you can calculate that. But what's the shortest distance on a sphere, like the Earth? That's a straight line. No. You go right off. Well, you can't go through the Earth. Definitely, there's not, if you want to go through the Earth, you're definitely not going in the shortest time. All right? So how's the shortest distance on Earth? You guys know? Yeah, it's like some circle. right? Which circle? How do you? Yeah, the great circle. Great circle, right? So you can imagine if you take 2 points, say Amsterdam and Boston, and you want to fly from one to the other, I do this a lot. Then you can go like this, or like this, or like this. But if you just take the globe and you take a piece of rope and you put them in between and you wiggle it while keeping it taut, right? Huh? You'll see there is some kind of curve at which you have the shortest distance. So sometimes called a geodesy. So you see this is a different geometry. The shortest distance is not a straight line. So there are new straight lines, right, which are now look like circles, but they're straight lines in the sense that they give you the shortest distance. Okay? So that geometry was called elliptical geometry. And also every line intersects every other line at 2 points, right? So all the great circles intersect at 2 points rather than 1 point or no points. Okay? It's an interesting geometry. Huh? And that's just the one we use, not really traditionally because we didn't go such long distances, but now if you fly an airplane, you definitely have to do. In fact, in the 16th century, they had to do it. It took them a long time, but they still had to find the shortest distance from here to Malacca or something, and it was the Great Circle. Of course, they couldn't fly, it gets a little bit, but when they're in the Pacific Ocean, then you have to find still then they have problems with winds. But, okay. Now this thing also has people thought that couldn't be possible. They actually tried to prove Euclid's last postulate, and they never could, and they realized it's only valid for very special. And then they found quantum geometry. And this is actually the geometry of space-time economy. It's a very interesting geometry. It's used in Smith charts and other things. Anyway. So what we see here is there's a lot of ways of picturing this that can be used in different forms of capital. All right? Whether it's growing, amortizing, or just closing. All right? So what we've done is we just created a nice picture, a geometric picture for this, all to be able to do dynamics, right? Because you need to have angles, you need to have kinematics to then derive your okay? But it's just interesting to see the history of these things and how it all comes together. What did I have here? Oh yeah, so here I have a banking application, the same thing. It's I just wanted to step through that. So the bank, they'll have three types of accounts. They have these checking accounts, and I'm not sure, but often these pay what they call simple interest, okay? I'm not sure, but anyway. Simple interest is interest that doesn't get reinvested in the account. It just gets paid out. Yeah, boom, is your interest. Bye-bye, okay? Then they have this is a savings account. They accumulate compound interest. So you have this money, but you get some money and it gets immediately reinvested in your savings account. That's what they do, all right? And every time you get an interest receipt, they reinvest it, and this thing starts growing. Okay, so savings accounts, they grow, all right? So this is a compound interest account, so it goes along this thing. So your total assets, if they start here, they can only be on these points here, along with hyperbola, okay? They can't be over here. Then you must have pulled out some interest or added capital or something, right? Huh? Okay. So if you add capital, you're another hyperbola, right? Okay. Uh-oh. These things, they are for things they call amortizing annuities. In Holland, they use this for homes, right? So if you buy a home, you get a mortgage, a hypotheek. And so first the bank gives you this mortgage. This is your principal of the mortgage, right? And then what happens? First year you only pay interest, or first day, right? Then first you pay interest. Then you have to repay a relatively small amount of the loan. Okay? Then you pay interest on the residual amount of the loan. Okay? Boom. And you repay a little bit bigger amount of interest of the capital, right? It's called a repayment. See that? Boom, 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 boom. And here, you know, all at the end, all of it is a repayment of the last tranche. Okay. So amortizing annuity, like a mortgage, they go along these kind of circular shapes. Okay. A little bit done differently. It depends on the contract. So sometimes these vectors are a little strange, they stick out. But you can imagine this being like a perfect amortizing annuity. It's called an amortizing. Because here you need to look at sums of squares or stuff like that. Okay, it's a slightly different mix. All right, and you can prove that a perfect one like this is actually a little bit easier on you, right? Okay? But what they do is they'll have a standard amount of payment, which is the sum of the interest payment plus the repayment, right? So this is V1 and this is V0, right? And this is the key constant. So if you look at the real trajectory, it looks a little funky. All right? Okay. And here you can think of this as the same way. So you keep the length of this vector constant, but you'll see it every time it consists of a different mix of interest payments and repayments of the loan. Okay? Yeah. Yeah, they look at it and start going like this. I don't know. You can do anything you like. Huh? Now, of course, in mechanics, who enforces this motion? That's just because this is a rigid arm, right? Now, who enforces this motion in banking? It's the contract, right? So the contract says you cannot deviate from this, okay? So the contract takes the place of the rigid rod connecting the origin, right, which is the 0.4 interest and capital, Now, of course, this rod can break, the string can break, or whatever it is, and of course, the contract can be broken, right? And then you need penalties. So if you have this thing rotating on, say, a string here, then there's going to be a normal force, okay? And so it's got to push back, and this contract has to do the same thing with penalties. It's got to kind of all the time force you to do this, right? Because you just want to keep going cruising on like this, and it's got to force you now. You're going to change your direction, right? Okay. So you're going to get all these centrifugal forces and all of this, right? You see that? Yeah, the bank really wants you to keep paying like that, right? But they know that that's impossible, right? Well, they also want their money back at a certain point. And what they really want is to have you pay interest. And as soon as they want their money, they want to do bond to you, right? That's what because they have another force that they got to add over this money. They want to stiff this thing to you, and they do sometimes. They have options, so you can build in these contracts all these weird options where now you're obliged to do this, and there'll be penalties associated with it. So all of these things can be translated into economic engineering. These penalties are another stream of flow. Boom, okay. So you can get very complicated contracts, and you can just analyze them. There's so much rotational motion, so much this, so much that. I mean, if you have a real pendulum, or probably that if it, this rope will stretch a little bit. I don't know. You get a little spring here, right? Huh? You get all these centrifugal forces. That's what they say. They call that repayments, I think, or what do the bank calls that? Where you make an extra payment, repayment?
Yeah, repayment.
Prepayment, yeah. So you're allowed to go a little bit in here, but it's a little bit like you have you suspend, say, a particle from a little bit elastic rope, so it can go, once in a while do a little movement. Yeah, it's fun to analyze these contracts from a mechanical point of view. So you can make this movement as complex as you want, of course. But the thing you got to see is that what these contracts do is enforce some kind of sub-manifold on which the thing has to go. All right? And then that's the kinematics of it. And then we can use a new set of coordinates called polar coordinates to keep track of how much capital you have and how much yield you've made. And the yield here is a combination of interest and repayments. This is your receipts, okay? And then you can use those coordinates to analyze it. And what's fun is they correspond to exactly what people do in finance, they call that the rate of return or the yield or the whatever they call, right? Okay. Now, in the case of these chicken and eggs, it's of course nature itself that is enforcing the constraints, okay? So these chickens just die, okay, after so many eggs. So, they become infertile, I don't even know. So nature just enforces the constraints. Now you can try to breed super chickens that don't die. You can do all kinds of things, and then there's a different constraint, okay? Okay, you can have a longer rope that you attach your bulb on, your mass on, all right? Okay? So you see the analogy is pretty good, So you can have this vector v, and then I can decompose it like in 1 here, that's v1, and then this will be v0, right? Now, this v1, that's an interest receipt, right? Okay. And this v0, those are the repayments for this case. And here, these are the reinvestments. Okay. So you can see, you can do some interesting geometry because here these reinvestments, they go with the repayments go with the sign, right? So it's a change of the cosine is this thing, all right? And this goes with the change of the cosine, which is minus the sine, right? So here you go, all right? Same thing here. This one, your balance is the cost, R times, this is your capital times the cost of all those returns. Did I use theta? Yes. Right? And then you take the derivative of that with respect to theta. All right. Now, I don't think anybody at a bank or in economics has ever done trigonometry, or actually, they don't use trigonometry in economics. I've never seen anything. Huh? Have you ever seen a cosine in an economic text? I don't think so. No, they use math, but never trigonometry. We do it all the time. I mean, first year, there's cosine. They even teach you these things without any application. So this is a nice way to translate these things in something that you can picture and set of tools. Again, this is just kinematics, right? We'll get to the dynamics. Let's first get ourselves in a familiar place with the kinematics. Okay? I'm thinking if there's anything else I want to say about the slide, but I think it's getting pretty clear, right? Huh? Okay, let's move on. Now I want to do something a little bit ambitious, but nevertheless, something very beautiful and very insightful. And I want to talk about the exponential map. Now, the exponential map is a vast generalization of what we normally think of as the exponential function. All right? So you know what the irregular exponential function is, you just do e to the power of something, right? And this thing was actually invented or discovered, or however you want to call it, in finance, you know? That's where it first appeared, strangely enough. Now, we took this thing over, of course, and we as engineers, we made great work of the putting a little I in front of this, where I is an imaginary number. Right? So we use these complex numbers. So we took this exponential map and changed this number for a real number into an imaginary number. Now, in the beginning, you think, what the heck happened there? How do I even calculate this? Okay. But after a while, you do some exercises, and they give you Euler's theorem. It's just the cosine plus I times the sine, blah, 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 blah. And you get so used to it, you don't even think about it. A polar, that's exactly a polar representation of a complex number. And you sit there, and you have your transfer function, and your Bode plot. There were complex numbers everywhere, all right? But somewhere along, somebody replaced that real number that is totally clear what it is with an imaginary number, and boom, what happened there? Now, it's another thing you will see when you do controls is that some types, they even put a matrix here. This is a matrix. And they take the exponential to the power of a matrix. How do you do that, right? Well, don't panic, they say. Just expand it in the Taylor series, 1 plus at plus a squared t squared or something, divided by 2 factorial, right? And then you know what matrix multiplication is, sure. So I just plug it in, and that's what it is, right? Okay. I have no intuition with it, right? But you just do it, and you realize there's no need to panic. You just use the Taylor series, right? You get on with it. What did you say?
Exactly control theory.
That's exactly control theory, right?
I don't know.
Yeah. I had no idea what's happening, but
Just learn the rules.
Yeah, you learn the rules. Yeah, that's it. So I want to change this. So what I want the exponential map is a map where you just take something totally weird, we'll stuff it in there, and you get something. All right? And I first want to say what it does, and then show you how this thing really works, get you the intuition. Okay? So here is how it works. So I put this return here, and rather than put omega, I put a big omega here. So this big omega can be just about anything. It can be a number, omega, right? I don't care. Right? It can be a complex number. It can be this. It can be a matrix. It can be tensor. It could even be worse. It could be vectors or functions, or I don't know what, right? We'll keep ourselves to here to just complex numbers and matrices, all right? But that's the idea, just, Now, here's an example of a complex number, but here's another example. Here it's a tensor, and it's a tensor that is skew symmetric. So you have some matrix, and then you have here some numbers, omega 1, omega x, minus omega y, and then here you kind of make it skew symmetric. So if you take the transpose and put a minus sign on it, you get the same thing back. All right? Okay. Anybody recognizes where they use these for, these skew symmetric matrices? You remember? Angular velocities, huh? Because you have a rotation matrix. You know what that is with cosines and sines? You take the derivative, you get the angular velocity matrix, okay? And that's a skew symmetric matrix, okay? All right. These are the pictures. I'm going to go through it. But here's the first, let me tell you what is in there. Here is the one you know, right? I just threw in, I just called big omega I times a real number, little omega, right? So this just, So then I look at the exponential map, And here I get this complex number, right? You all know that. I do e to the power of this times t, and then I get some complex number z. Huh? All right? Now, what's going on here? All right? What's going on here? I want to explain that to you. Interestingly enough, this is the most intuitive one. And that's why it's called a map. So here I have a map, and I always forget what this map is called, but you see it in the emblem of the United Nations like that. And it's called the azimuthal equidistant map or something like that. But this is how it works, okay? So you go and sit, in this case, at the North Pole, and then you look at a unit, a certain velocity, angular velocity, omega. Okay, so you have the radius of the Earth, angular velocity, and you just go and go along the Earth like that. And you just start, lopping off these areas, and you plot them over there, right? So these are all different directions you're going to. Here's one, here's the direction, here's the direction, all right? And if you do that, you'll create a map like this, okay? Okay? This is good. So this thing is the actual distance you'll travel as you go along the Earth, in that direction, along that line of longitude, all right? Huh? And here you can see also that these lines of latitude are all equidistant now, right? As they're supposed to be, okay? So this is an angular velocity, and if you integrate that out, you'll get this map, and it's precisely, this thing is then, this angular velocity tells you exactly how fast you're going, and the exponential map, what it does, it gives you, this is the longitude, and this is the latitude. It gives you this point, right? So you follow it along. That's what happens. So the exponential map just tells me how to calculate the arc length along the path I'm taking. That's what it does, all right? Okay. Is that clear? You have to accept that now. I can derive it, but I don't want to do that. But I'm going to do it for this very simple case, okay? So this is just the intuitive thing where it comes from, all right? And this was done already a long, long time ago. I think even the ancient Greeks, they made maps like this. I'm not quite sure, okay? So they have this idea of just like measuring or keep walking, and then, all right? Huh? And they didn't have the exponential map yet, but that's what they were doing, all right? Now let's look at the complex exponential that's familiar to you. I stole this picture just from the internet just to give you the idea of how they would explain it. But here you can recognize your amortizing, your amortizing capital, all right, resources, amortizing resources. And here you recognize the fixed resource, okay? And what you have to imagine is that if it's amortizing, you kind of, and you have it, the units line up, what you're trying to do is say, well, what's the equivalent amount I'm receiving if I were going along this line, right? So what I'm going to do is I'm going to take this axis here and just wrap it around, this is like a little rope, and I can calculate the length, and I just wrap it around, and then I can see how much distance I've traveled. All right, that's the idea. Okay, you follow that? So that's just a way of measuring. See, what's the length of this thing? Right? How are you going to measure that, right? Well, you can say that's a radian. So what I did with a radian, I took the radius here, and I just kind of fit it in there. So what I do is I take little steps like this, and I'll put it over there, and then just fit it in there, right? Huh? That's a radian. Okay? Calculate how much it is. You can calculate that there's 3.14 of these fitting in there. This is 1, 2, 3, and there's a little bit left. Right? That's number 5. Anyway, now what do you do? What is this line? Well, really, this line is the line 1 plus I times t, right? Because you're sitting here at 1, and you keep going up in this I direction here. This is the complex plane now, all right? Huh? Okay. So what I did is I put those eggs on the imaginary axis. I put the chickens on the real axis. So I think of eggs as just imaginary chickens, okay? I mean, they're real enough, but they still have to hatch, and then they're real chickens. So I don't want to count my chickens before they're hatched, as the saying goes. So I call them imaginary chickens, all right? Yeah? And that's what you do, all right? Okay? Now this works out. This is the exponential map. So if I go up to t, so here this is really omega t. They just use an omega of 1. Okay? These are mathematicians. You'll end up here. This is how it works. Okay? Now why is that the case? Right? I mean, why is this the exponential map? Let me show you why that's the case. So normally what they do is they tell you, okay, this all works because this is the Taylor series, right? You start doing this in the Taylor series. Now, if I plug in I omega for this, I'm going to get a Taylor series. You know how it's going to look? The Taylor series will look like this. So I got 1 plus, this is the first term, okay, I. And then here I get an I squared, so that becomes minus 1. Here I get I to the third, that's minus I, all right? And here I get another, you see? So it keeps flipping. So I have a positive real 1, a positive imaginary 1, a negative real 1, a negative imaginary 1, and then it, okay, turns around. You follow that, right? Huh? Okay, what's happening? What's happening here? So I have 1. That was the first term, right? Then I have an imaginary term. Here, boom. Then I have a negative real term, okay? Because this I squared is minus 1. Then I have a negative imaginary term, right? And I keep going on. Chop. There I am. Okay? So what am I doing economically? Okay, I got this chicken. I got so many eggs. So many chickens died, right? Huh? So many eggs are starting to hatch. Okay, another few chickens less, much less. How much less? I think it's 3 factorial or something. This 2 factorial, no, this 3 factorial, this must be 4 factorial. 1 divided by 4 factorial, right? This is 1 divided by 3 factorial, right? Let's go on. And if you want to go, you can't, of course, divide the chickens into gazillions, but if you would do that, you will end up the whole Taylor series and you will go there. That's what you call continuous compounding, okay? You see that? Okay, started with the chicken, get some eggs, some chicken die, half of them. Okay, you divide by 2 factorial is 2, right? Then 6 of these, what is it? 1 divided by 3 factorial is a 6 of the egg starts having, okay? Interesting, no? So you see also here why I squared has to be minus 1, right? Because suppose you get your chicken. Now these chickens are these you get these eggs. They're imaginary chickens, okay? And then the next rotation, so every rotation is multiplying by I, you've got to get a chicken to die. So you've got to get a negative number, you see? Huh? So you got to have that I squared is minus 1, all right? Then the next rotation of 90 degrees, that's this term, you got to get that negative I, So what's happening is if you go from here, you do a 90-degree rotation, you get I, and here you do another 90 degrees rotation. So this must be I squared, but that's minus 1, and then you just go through like that, okay? So there's nothing imaginary about I squared being minus 1. All it's saying is that if you first get your eggs and then, and then you start hatching them, you're going to end up, in the same meantime, these chickens have died, all right? Okay, or geometrically, 2 90 degrees rotations is I times I should be minus 1, is a 180-degree rotation, okay? All right? So the normal way in which you get taught the number I is to say it's a strange number that when you square it, you get -1. But what they never say is that I is a 90-degree rotation, and if you and -1 is a 180-degree rotation, and if you do two 90 degrees rotation, you're going to get 180 degree, right? Huh? Okay. Yeah, sure. All right. So we're using these complex numbers now to start moving around in our capital return plane. You know, it's very efficient to do that, you know. And then we can use this exponential map to calculate, you know, how much we've been traveling. So how much money we have received in total, okay? All right, and where we ended up, okay? So we can calculate this arc length. So that's what the exponential function does here, and that's exactly what it will do here. It will just calculate how much you've traveled. All right? Okay? It's a wonderful thing. That's why you see it everywhere. All right? Because you want to go from your velocity to your position. So you want to go from your yield to your total amount produced. So you got to integrate that out. But integrating out in a weird space is difficult because the thing is turning on you. So you got to use the exponential function. Now you asked me if I in a flat plane, why am I not using the exponential function then? But you are, and we'll come to it. That's also the exponential function. All right? Huh? Okay. Now this seems a little bit of a side note, but you'll see that if you see it from this point of view, all the theory of capital and its kinematics will be brought together in one kind of picture, okay? So in finance, they talk a lot about exponential growth, but what we can do now is to say, well, amortization is also exponential, okay? And this is also exponential. Everything is exponential. You just use a different exponential, all right? So we can keep the concept of exponential growth and then generalize it, all right? This is actually what group theory does and what Lie groups do. They take this idea and they push it to this type of limit, all right? We're going to take a little bit of the things you're familiar with and you will need, but rest assured this can be generalized to a very large degree. And it just cleans up your mind. Otherwise, you have all these different things lying around, you know? It just becomes all, you know, typical engineering. You just learn that, remember it for the exam, do the exam, and then walk out again and forget about it. Huh? All right? And how are you going to do research? Okay? Clear? So let's start doing this. So what I want to do is start exploiting complex numbers. So this is really something you're familiar with. The other two motions, so this one is familiar with. I want to now show, and this one is also exponential. I want you to show you why. And this one also, all right? I want to do it there, all right? That's what I want to do for the remainder of this lecture, okay? All right, let's go do it. So instead of using these Q0 and Q1 coordinates, we're just going to use we're going to think of this capital return plane as a complex plane, right? And we're going to have three complex planes. For amortizing capital, we use the normal concept, complex plane, and we'll have some complex number, and we'll put the capital on the real, so capital is real, and the products are imaginary. And I have three types of imaginary numbers, but for amortizing, you have this one, and for compounding this one, and for shearing or just fixed capital will be this one, all right? Now, then you can find out that your capital is just a norm, right? No problem, okay? This is the complex conjugate. So what's the complex conjugate? You got the same type of capital, but instead you had a negative return, right? So you were short. You were just short, okay? So you can think of that as a hedge. If you add them up and divide them by 2, you're just going to be, be here, okay? If you multiply them. And if you multiply them and you take the square root, you know, you're just going to get this, the capital itself, okay? So think of the conjugate as a hedge. the thing that hedges out the return. All right? So you have a set of securities, and you're getting these dividends, and you go short half of it, right? Then you multiply these together, you take the square root, and then you get the total number of capital you have. Okay? Huh? Now, complex numbers, you know, here it is, and the I squared is minus 1. We went through this. This thing is just that, and then you can calculate the radius. But now we can have some other numbers. So let's first look at what are called split complex numbers. They're very interesting. So I'm going to go back to, let's go back, let's do it here. So here, remember, with the complex number, you go up first, and then in the Taylor series, you have to go left because I squared is 1, right? Minus 1. Here, we want to do the opposite. We want to go up, right? So call this the j-axis. I don't want to use I because I use the next letter J, right? And instead of going left, I want to go right. So what I need to do is that j squared is 1, right? Okay. Now you say, look, if j squared is 1, j is 1. No. Don't make that mistake. Because j squared is 1. J is the product. Only when you do another time step will that be reinvested. Okay? So multiplying by j means generating the product. Multiplying again by j means a reinvestment. Okay? All right? So don't think that's 1. If you have a square and the area is 1, then the sides are also 1, but they don't have the same dimensions. These are in meters and these are meters squared. It's not that, it's the same thing. You got to be a little bit careful that if j squared is 1, the other is 1. No. Huh? Huh? Okay. So if you do that, okay, then and you use your Taylor series, then what's going to happen? Then here, I worked out the Taylor series, right? So I'll, every time I have a j instead of an I work through the whole thing, and I get this thing, okay? Now, if I recognize this, this is just this. Huh? All right? So this is exponential growth. This is the regular exponential where you just put j omega here, all right? This is normally the formula for compound interest, right? So here's the 1, the r is this p, and here's a little r, that's omega, because that's the interest rate. However, I put the j there. Why? Because I want to go in the j direction. I don't want to go in the real direction, okay? Because I'm getting interest. Interest is different than capital, okay? That's the only change I made to this compound interest formula. And then I put NT, and I worked it out. Okay? Then I get this Taylor series, and if you look it up, you'll see that you can split, you can take all the real parts, put them together, you get the Taylor series of the cosh, and you get those, and you get the Taylor series for the sinh, you get the j in front of it. So this thing is r cosh omega t, and this is r sinh omega t. So the interest goes with the sinh, and the capital grows with the cosh, okay? This follows out of our Taylor series, but it also follows out of the idea that this works. All I did was, just with the complex case, just kind of step through what's happening, okay? I start with my investment, I receive some interest, I reinvest it, okay? Divide by 2, good, huh? All right? Say, go on like that. All right?
I have to go.
So here you see, this is the old-fashioned amount, the old-fashioned way in which in finance you look at compound interest. And if you do it in a continuous time, you just take the limit as this goes to infinity. You get this formula. All right. So with this, I've shown you that this whole idea of reinvestment is a hyperbolic motion. Okay. But this is a little bit better by keeping the j in there because we're keeping track of the interest accumulated and the capital, this is what you got to do, because interest gets taxed differently, the capital gets booked differently, all right? So the accountant will keep these separate, okay? So if this is property, plant, and equipment, this will be your initial capital. That is conserved, so your initial capital doesn't change. So if you, so it's even better. If you just have a company, you'll have some initial capital. That's what you deposit. So you put that in, and then you get earnings, okay? Then you can retain those earnings. That means you add it by your capital. But in the books, you still have to separate the initial capital from the retained earnings, okay? And then these companies, they can experience exponential growth because everything that come in, that they reinvest it. So you go through this Taylor series and you walk your way along this hyperbola, all right? Now, if you add this up, so if you look at this actual amount here, that will be indeed, you know, what is it? Cosine, sine, and you look at this, square root of 2 times something. But that's only if you don't keep the interest and the capital separate, okay? You need to do that. You need a separate port for it, okay? All right? Now, here's now the beautiful thing. So everybody, of course, is comfortable with that you have, that this is a compound interest and growing capital, but as soon as they have amortizing capital, they don't use the exponential function anymore. So they don't use the exponential. But we know better. We can just write down the same formula. Here's the capital. Here's the rate of return, right? You'll plug it in, and there is your formula. This is called Euler's formula or something. He's got so many formulas, I never know whether it's a formula or a theorem or a rule or a whatever. And now you see that your capital, your resource, your chicken resource is on the cosine and your egg resource is on the sine, right? Okay. I should have done this. Okay. And it's, you have to multiply by I because we're in the complex plane, and this is the I axis. So it's exactly the same. See, that's why we do these things. It's just the same. I don't have separate, you know, how would you do this as an economist or accountant? You would just have a large table. They have large Excel sheets and tables of how these amortizing loans go, right? There's no formula, right? There's no recognition that this is also exponential growth in a sense, but it's imaginary, all right? Okay. All right. Okay. Actually, I put this formula here. I made this slide a while ago. This is considered one of the most beautiful formulas in the world, right? And always a bit mysterious. Well, because, you know, it has all these numbers, like minus negative numbers, imaginary numbers, pi and e. And why did I put it here? Well, because really, yeah. So this is 180 degrees, right? Rotation. Rotation. This is a rotation over. So all that's saying is that that's given by the angle pi. So you can also say, like you did, is that there are two rotations of half pi, right? So you do e to the yeah, is minus 1. That's what you said. So you said two rotations. But why did you say that? You were a little bit unclear, but the reason is this is the number I, right? Of course. And this is the number I. So then it just says I squared is minus 1. But really it's not even saying that. It's saying something even easier, right? It's just saying that pi is the angle at which you are, you know, that you need to rotate, rotate to get a flip, right? Because going from positive to negative is a flip, right? So that's all it says. So all of a sudden, nothing is magic anymore. You know, that's kind of where I want to get you guys at, right? Huh? You know, just look through the formulas, see what it tells you. All right. I guess that's why I put it there. All right. So this formula also, I just wanted to put it here to show you that it's just a way of going through the Taylor series, and we'll get the hyperbolic cosine and sines. Okay. And I have a few more minutes, and I now want to do something they are called dual numbers. So these other ones, these are called split complex numbers. These are regular complex numbers. These are called split complex numbers when you have j squared as 1. But you have another set of numbers they're called dual numbers. So you either have I squared is minus 1 or I squared or j squared is 1. And what's the other option? 0, yeah. So you have these dual numbers, and we use epsilon for that because we assume that epsilon square is 0. All right? Now that's very typical, right? So that's when we do these kind of calculations of small variations, and we assume that if it squares, you ignore them, right? Huh? That's why I use epsilon here. Okay. But what's really happening when you look at, say, simple interest? So I get epsilon r epsilon t here, right? Huh? Or whatever I got. We're going at what this should be is epsilon times omega. And then after another epsilon, what is going to happen? Am I going to go right? No. I'm going to go left? No. Just epsilon squared will be 0 because I'm not going anywhere. Okay. So I just have a nice algebra is that they add up, but when I multiply them, nothing is going to happen. They're neither going to amortize nor are they going to grow. All right. So all it says is no growth, no amortization. Okay. There's nothing evolving. Okay. So you know what? Why don't we just plug it in here, right? Okay. So you plug this in, you work it out, the Taylor series. So this is just your compound interest formula, right? And what do you get? Well, you get 1. Then the first term shows up, right? There you go. And then you get a square term. Well, it becomes 0, right? And then the third term. So almost 0, right? So what are you left with? Is it just this? Right? But this is exactly that. Okay? And you can think of this as sort of a cosine plus a sine. And this is exactly what's happening. So the cosine is always 1. And the sine is just proportional. Huh? Okay? Right? Nice and simple. So even this is just a regular displacement. You're here, or you're just going up this way. You just write it as an exponential function. The thing you got to realize, this is amazing. This function can do anything. As long as I'm going along a one-dimensional manifold, I can do that. For higher dimensional manifolds, I maybe need tensors and matrices. That's just what it does. All right? Just tells us how far we've traveled. Okay? You can use the same idea over and over again. All right? Okay? So I showed you these 3 examples. These are all famous because complex numbers, of course. These are the split and the dual complex numbers because they corresponded to these different type of geometries. So complex numbers to spherical geometry, dual numbers to just the shears, you know, and then these split complex numbers to relativity, to these boosts, I call them. All right. So I did this, and they're all interestingly, now you can find this is the simple interest formula, right? It's just there. All I did was make sure that I have an epsilon axis in which the interest is accumulating, right? But I can't get interest on interest. And I can't have my capital die after, would get taken out after I've received interest. So epsilon squared cannot be minus 1. That means my capital is amortizing. They're taking it out. No. And epsilon squared is 1. That means it's growing, and it isn't. All right? It's just not happening. All right? So, but it's kind of, you see, just keep your head screwed all right, and everything looks exponential. There's a big theory called Lie group theory, and this is the basic idea, that you have an arbitrary manifold, weird space, and as long as you have some kind of tangent vector somewhere, a bunch of tangent vector, that's called the Lie algebra, you can follow that along the manifold and calculate where you are. And that map is called the exponential map. It's a very general theory, all kinds of proofs. We won't need any of it, but that's the idea. All right, that's the idea. And that's the same thing that gets played in controls when you take a matrix exponential. You know, they have some rate at which things are going, and you just want to, you know, that's the A matrix, tells you what your rate is, you know, x dot is AX, and then you want to find out where you end up, right? So you integrate out, so you take the matrix exponential, okay? If you have linear equations, they show up all the time because they're the solution. So you see, well, that's it. With this, I want to end this lecture. So we did all the kinematics, and then next week we're gonna do dynamics with these things, do the pricing, add the kinetics to it. Okay. All right.